The unthinkable pipeline. The pencil scratches were the only sound in the dimly lit room as Bernard Ellis bent over the blueprints, his shirt sleeves rolled up despite the London chill of early 1942. Around him, three other men studied the technical drawings with the intensity of surgeons examining a patient's heart. What they were contemplating seemed impossible. A pipeline beneath the English Channel, carrying fuel to armies that didn't yet exist, for an invasion that remained little more than Churchill's audacious dream. Ellis adjusted his spectacles and traced a finger along the cross-sectional drawing of what would become one of the war's most extraordinary engineering achievements. The Anglo-Iranian Oil Company had tasked him with solving an unthinkable problem. How do you fuel a mechanized army fighting hundreds of miles from its supply bases? How do you guarantee that Sherman tanks won't run dry of petrol just as they're breaking through German defensive lines? The answer lay in the seemingly mad concept spread across these blueprints. Operation Pluto, pipeline under the ocean. In that quiet room, with only the distant hum of London's wartime activity filtering through blackout curtains, Ellis and his team were designing something that had never been attempted. Not just a pipeline underwater, but a pipeline that could survive the crushing depths of the Channel, the corrosive effects of salt water, and the very real possibility of German interference. They were essentially trying to build an underwater umbilical cord that could keep an entire invasion force alive. The technical challenges were staggering. Standard pipelines were rigid, designed for stable ground, but the channel floor was anything but stable. Shifting sands, rocky outcroppings, and the constant movement of one of the world's busiest shipping lanes. The pipeline would need to be flexible enough to move with the ocean floor, yet strong enough to maintain pressure across 20 miles of underwater terrain. Ellis had spent weeks studying submarine cable technology, borrowing concepts from the telecommunications industry. The solution, he believed, lay in creating something entirely new, a hybrid between a pipeline and an underwater cable. Steel tubing wrapped in protective layers, designed to flex and bend without breaking, capable of carrying thousands of gallons of fuel per hour across the Channel's treacherous waters. But theory was one thing, manufacturing was quite another. The Siemens Brothers factory in Woolwich had never seen anything quite like the order that arrived in the spring of 1942. Workers accustomed to producing telephone cables found themselves retooling their entire operation for something far more ambitious. The factory floor, usually organized around the precise requirements of copper wire and rubber insulation, now echoed with the sounds of steel pipe production and pressure testing. Arthur Hartley, the factory's chief engineer, walked the production line each morning with a mixture of pride and anxiety. His workers were manufacturing what amounted to the world's longest fuel line, mile after mile of specially designed pipeline that would either revolutionize military logistics or become the most expensive failure in engineering history. The manufacturing process was unlike anything attempted before. Each section of pipeline began as high-grade steel tubing, carefully tested for pressure tolerance and flexibility. This core was then wrapped in layers of protective material, tarred hemp, lead sheathing, and finally an outer layer of steel wire armor. The result looked more like a massive electrical cable than a traditional pipeline. Every 100 yards of completed pipeline had to pass rigorous testing. Workers would seal both ends and pump the sections full of water under pressure, checking for even the smallest leak. A single weak point could doom the entire operation. Imagine thousands of gallons of precious fuel hemorrhaging into the Channel while Allied forces ran dry just miles from their objectives. The workers understood they were building something important, though the full scope remained classified. They knew it involved the invasion everyone whispered about, the second front that would finally bring the war to Hitler's doorstep. But the specific details of Operation Pluto remained locked away in the minds of a handful of engineers and military planners. Hartley often found himself standing before the massive winding machines that coiled the finished pipeline onto enormous drums. Each drum held miles of pipeline, representing months of precise manufacturing. The sight was both impressive and humbling. Here was the physical manifestation of Britain's determination to make the impossible possible. The secrecy surrounding the project created its own challenges. Workers couldn't discuss their work outside the factory walls. Suppliers received only partial specifications, never seeing the complete picture of what they were contributing to. Even within the factory, information was compartmentalized. The men operating the steel-forming machines knew nothing about the pressure testing protocols. The quality control inspectors understood their specific tolerances, but not the broader engineering requirements. This security came at a cost in efficiency, but it was absolutely necessary. German intelligence networks were actively seeking information about Allied invasion preparations. A single leaked detail about underwater fuel pipelines could compromise not just Pluto, but the entire D-Day operation. As winter gave way to spring in 1943, the first completed sections of pipeline began arriving at secret testing facilities along the English coast. The theoretical had become tangible. Coils of steel and protective wrapping that represented humanity's first serious attempt to create a permanent underwater fuel supply line. The testing phase revealed both the brilliance and the limitations of the design. Short sections performed beautifully in controlled conditions, maintaining pressure and flexibility exactly as Ellis had calculated. But longer sections, subjected to the real-world conditions of tidal currents and shifting seabeds, presented new challenges that hadn't appeared in the blueprints. Salt water proved more corrosive than anticipated. The protective layers, while effective against pressure and physical damage, weren't quite sufficient to prevent the slow but steady degradation that came from constant exposure to the channel's harsh environment. Ellis and his team found themselves redesigning protective coatings, adding additional layers of defense against the ocean's relentless assault. The flexibility that made the pipeline viable also created unexpected problems. Sections that bent too freely under current pressure experienced stress fractures at connection points. The engineering team had to develop new joining techniques, methods of connecting pipeline sections that could maintain perfect seals while allowing for the constant movement of underwater installation. Each problem solved revealed two new challenges. The pipeline needed to be heavy enough to stay on the ocean floor, but light enough for ships to handle during installation. It required enough flexibility to follow the channel's contours, but sufficient rigidity to maintain its shape under pressure. The protective layers had to guard against corrosion, physical damage, and the possibility of German sabotage attempts. Meanwhile, the clock was ticking toward invasion. Military planners were finalizing logistics for what would become the largest amphibious assault in history. Fuel requirements were staggering. Thousands of vehicles, aircraft, and ships would need constant supply once the invasion began. Traditional methods, tanker ships and fuel trucks, would be vulnerable to German attacks and insufficient for the scale of operations planned. Pluto wasn't just an engineering challenge, it was becoming a strategic necessity. The pipeline represented a new kind of warfare logistics, one that acknowledged the industrial scale of modern military operations. Previous conflicts had relied on relatively simple supply lines, horses, wagons, and basic fuel depots. But the mechanized armies of World War II consumed resources at unprecedented rates. A single armored division could burn through thousands of gallons of fuel in a day of heavy fighting. Ellis often worked late into the evening, refining calculations and reviewing test results by lamplight. The responsibility weighed heavily on him. Millions of Allied soldiers would depend on his engineering decisions. The pipeline had to work not just in theory, not just in testing, but in the chaos and uncertainty of actual combat operations. As 1943 drew to a close, the Pluto project had evolved from an impossible dream into a manufacturing reality. Miles of pipeline lay coiled and ready, representing thousands of hours of precise engineering and manufacturing. The testing had revealed problems, but it had also proven the fundamental concept. Fuel could be pumped across the channel floor, maintaining pressure and flow rates sufficient for military operations. The next phase would be even more challenging, actually laying the pipeline across 20 miles of ocean, connecting it to pumping stations on both sides of the channel, and making it operational in time for the invasion that everyone knew was coming. The engineering problems were solved, but the logistical and operational challenges were just beginning. In factories across Britain, workers continued their precise, secret labor, manufacturing the components that would make Operation Pluto possible. They worked with the quiet determination of people who understood that their craftsmanship might determine the outcome of the war. Every weld, every pressure test, every quality control check was performed with the knowledge that Allied lives depended on their precision. The unthinkable pipeline was becoming reality, one carefully manufactured section at a time. HIAS, a cable of hope. While the steel pipe sections took shape in British factories, another group of engineers was pursuing an entirely different approach. Arthur Hartley, a brilliant cable specialist at Siemens Brothers, had spent decades perfecting the art of submarine telegraph cables. Those delicate copper lifelines that carried messages across ocean floors had made him intimately familiar with the challenges of laying flexible conduits beneath the sea. Hartley understood something that the steel pipe engineers were still learning. The channel was not a static environment. Tides surged back and forth with tremendous force. Storms could shift the seabed itself. Any pipeline would need to bend without breaking, flex without failing. His solution was elegantly simple in concept, fiendishly complex in execution. Take the proven technology of submarine cables and scale it up dramatically. Instead of copper wires carrying electrical signals, he would create a flexible steel tube carrying liquid fuel. The HAIS cable, as it came to be known, taking its name from Hartley Anglo-Iranian Siemens, would be 3 inches in diameter. That might sound modest compared to modern pipelines, but in 1943, creating a flexible oil conduit of that size represented a manufacturing challenge that pushed every boundary. Cy Appleyard, Hartley's colleague and co-conspirator in this ambitious venture, brought his own expertise in materials science. Together, they faced a fundamental problem that had never been solved before. How do you create a pipeline that's strong enough to withstand ocean pressures, flexible enough to coil like rope, and chemically resistant enough to carry petroleum products without degrading? The answer lay in layers, multiple concentric shells, each serving a specific purpose. The innermost core would be lead, chosen for its complete resistance to petroleum corrosion. Around that, they would wind steel wires in a helical pattern, providing tensile strength while maintaining flexibility. The outer sheath would be more steel wire, wound in the opposite direction to prevent the cable from twisting under tension. But the devil, as always, lived in the details. The lead core couldn't be too thin, or it would collapse under external pressure. Too thick, and the cable would become impossibly rigid. The steel wires had to be precisely tensioned during manufacture. Too loose, and they'd provide no structural support. Too tight, and they'd crush the lead core. In the cable works at Woolwich, Hartley and Appleyard supervised the construction of entirely new manufacturing equipment. The extrusion presses for the lead core had to operate at temperatures hot enough to keep the metal flowing smoothly, but not so hot that it would affect the cable's final properties. The wire-laying machines presented their own challenges. These massive devices, spinning like industrial looms, had to maintain perfect tension on dozens of steel wires simultaneously. A single wire breaking during manufacture could ruin hundreds of feet of cable, and with the invasion timeline looming, there was no margin for waste. The workers operating these machines developed an almost supernatural sensitivity to the sounds and vibrations of the manufacturing process. A slight change in pitch from the wire-laying machine might indicate a tension problem. A subtle shift in the rhythm of the extrusion press could signal a temperature fluctuation that would affect cable quality. Quality control became an obsession. Every foot of cable was tested for pressure resistance, flexibility, and chemical compatibility. They would cut sample sections and subject them to accelerated aging tests, exposing them to temperature extremes and chemical baths that simulated months of service in compressed time. The testing revealed problems that sent the engineers back to their drawing boards again and again. Early versions of the cable showed a tendency for the lead core to develop microscopic cracks when coiled too tightly. The solution required adjusting the alloy composition of the lead, adding trace amounts of antimony to improve its flexibility without compromising its corrosion resistance. Meanwhile, the Royal Navy was grappling with an equally complex challenge. How do you deploy 20 miles of 3-inch cable across the English Channel? Traditional cable-laying ships were designed for much smaller telegraph cables. The weight and bulk of the HAIS cable would require completely different handling equipment. HMS Conundrum, a converted merchant vessel, became the testbed for cable-laying techniques. Her deck was dominated by an enormous cable drum, a steel cylinder nearly 20 feet in diameter, capable of holding miles of the heavy HAIS cable. The drum itself was an engineering marvel, designed to rotate at precisely controlled speeds, while maintaining constant tension on the cable as it fed overboard. The cable-laying crew had to learn entirely new skills. Unlike telegraph cables, which were relatively light and could be handled by small teams, the HI's cable required coordinated effort from dozens of sailors. The cable's weight meant that once it started feeding overboard, it would continue with tremendous momentum. Stopping the deployment process required careful coordination between the ship's speed, the drum rotation, and manual brakes that had to be applied with split-second timing. Practice runs off the British coast revealed the intricate choreography required for successful deployment. The ship had to maintain a precise course and speed, accounting for tides and currents that could pull the cable off its intended path. Too fast, and the cable would be laid with excessive tension that could cause it to snap under its own weight. Too slow, and the cable would pile up on the seabed in loops and coils that could block fuel flow. Navigation presented its own complications. The cable-laying ship had to follow a predetermined route with extraordinary precision. Deviations of even a few hundred yards could place the cable in areas where it might be damaged by anchors or fishing nets after the war. Back at the manufacturing facilities, production was accelerating as the invasion timeline solidified. The cable works operated around the clock, with 3 shifts of workers maintaining continuous production. The night shift workers developed their own rhythms and techniques, working by sound and feel as much as sight, guided by the steady hum of machinery and the subtle vibrations that indicated everything was functioning properly. Arthur Hartley made regular inspection tours, examining cable samples under powerful microscopes, checking the uniformity of the lead core and the precise alignment of the steel wire reinforcement. His trained eye could spot potential problems that might not manifest for months of service. A slightly irregular wire lay that could create stress concentrations or microscopic inclusions in the lead that could become failure points under pressure. The HAI's cable represented more than just an engineering achievement. It embodied a fundamentally different philosophy of warfare logistics. Instead of accepting the limitations of existing technology, Hartley and his team had created entirely new capabilities tailored to the specific demands of the invasion. As the first complete sections of HI's cable wound onto the drums of HMS Conundrum, the reality of Operation Pluto was taking tangible form. What had begun as a seemingly impossible concept was becoming a physical reality. Coil by coil, test by test, one carefully manufactured foot at a time. The cable gleamed in the industrial lighting of the Woolwich Works, a serpentine embodiment of British engineering ingenuity and determination. Soon it would rest on the floor of the English Channel, carrying the lifeblood of mechanized warfare to the beaches of Normandy. Hamel, steel under the sea. While Arthur Hartley's team refined their flexible cable solution at Woolwich, another group of engineers was pursuing an entirely different approach to the same impossible problem. Bernard Ellis, the brilliant petroleum engineer from the Burma Oil Company, had been studying the Channel crossing challenge from a different angle entirely, one that would require even more audacious engineering. Ellis understood that flexibility, while elegant, came with inherent limitations. The HAI's cable, for all its ingenuity, could only handle relatively modest pressures and flow rates. But the fuel demands of a mechanized army fighting its way across Europe would be enormous, far beyond what any flexible pipeline could reasonably deliver. What was needed, Ellis concluded, was something more robust, more permanent, more like the great oil pipelines that crossed continents. The solution he proposed seemed to defy every principle of marine engineering. Instead of a flexible cable that could bend and twist with the currents, Ellis envisioned rigid steel pipes, 3 inches in diameter, welded into continuous lengths, and somehow laid across the channel floor like an underwater railway. The technical challenges were staggering, but Ellis had identified something his colleagues had missed. The channel, for all its reputation as a treacherous waterway, was relatively shallow, and its floor, once you got past the immediate coastal zones, was surprisingly stable. The project that emerged from Ellis's calculations would become known as Hamel, named, with typical British understatement, after the 2 engineers whose initials it bore, Hartley and Ellis, 2 men approaching the same problem from completely different directions, their solutions destined to work in tandem beneath the dark waters of the Channel. But first, Ellis had to solve a problem that seemed almost comically simple, and yet proved maddeningly complex. How do you transport 3 miles of rigid steel pipe across 20 miles of open water? The pipes couldn't be assembled in place. Welding underwater was impossible with 1940s technology. They couldn't be towed as separate sections. The logistics would be nightmarish, and the risk of losing sections to enemy action or rough seas was too great. Ellis's solution was characteristically bold. The pipes would be welded together on shore into continuous lengths, then wound onto enormous floating drums. Like thread on a spool, but with each thread weighing several tons per 100 feet. The drums themselves would be marvels of engineering. Steel cylinders nearly 60 feet in diameter, designed to float while carrying thousands of tons of pipe. During the crossing, the drums would be towed by tugboats, unwinding their precious cargo directly onto the seabed. The mathematics alone were daunting. The pipe had to be wound with precisely calculated tension. Too loose, and it would tangle during deployment. Too tight, and the steel would deform under its own weight. The drums had to maintain perfect buoyancy as they gradually lightened, their centers of gravity shifting constantly as the pipe unwound. And all of this had to work in the middle of the English Channel, with German coastal artillery potentially within range. By early 1943, construction had begun on the first Hamel drums at shipyards across Britain. Each drum required nearly as much steel as a small warship, and the precision demanded was extraordinary. The welding alone took months. Each joint inspected, tested, and retested. A single weak point could doom the entire pipeline, leaving thousands of Allied vehicles stranded without fuel on the far side of the channel. As the drums took shape, attention turned to the shore installations that would make the system work. Unlike the Hayes cable, which could theoretically be operated from relatively simple pump stations, Hamel would require substantial infrastructure on both sides of the channel. The pipes were rigid, the pressures high, and the flow rates enormous. This wasn't just an engineering project anymore. It was industrial infrastructure on a scale that would be visible from the air. The British terminal was established at Dungeness on the Kent coast, a desolate stretch of shingle beach that had the advantage of being both close to the channel's narrowest point and relatively isolated from prying eyes. Through the summer of 1943, construction crews worked around the clock, building what appeared to be a small industrial complex. Pump houses rose from the shingle, their brick walls designed to withstand both German bombing and the corrosive effects of salt air. The pumping stations themselves were marvels of precision engineering. Each housed massive centrifugal pumps capable of pushing fuel through miles of underwater pipeline against the resistance of seawater pressure and pipe friction. The calculations were complex. Too little pressure, and the fuel would never reach the French coast. Too much, and the pipes would rupture under the strain. The engineers had to account for temperature variations, tidal effects, even the slight changes in pipe diameter that would occur as the steel expanded and contracted with the seasons. Storage tanks appeared next to the pump houses, great steel cylinders that would serve as buffers between the overland fuel supply and the underwater pipelines. The logistics were staggering. Hundreds of thousands of gallons would need to flow through this system daily once operations began. Tanker trucks would arrive continuously from refineries across southern England, their precious cargo disappearing into tanks that fed the hungry mouths of the Channel pipelines. But perhaps the most remarkable aspect of the Dungeness installation was how ordinary it looked. From a distance, it resembled nothing more than a modest fuel depot, the kind of industrial facility that could be found near any major port or airfield. Only the massive concrete foundations and the unusual number of pipes running toward the sea hinted at its true purpose. The camouflage was deliberate. German reconnaissance flights passed over regularly, and anything that looked too important would inevitably attract unwelcome attention. Across the Channel, similar preparations were underway at sites along the French coast that remained for now in German hands. Allied intelligence officers studied aerial photographs and resistance reports, identifying suitable landing points for the pipeline terminals. The beaches had to meet strict criteria, accessible to the pipeline-laying ships, defendable once captured, and close enough to existing road networks to support the massive fuel distribution system that would be needed. The French terminals would be even more challenging than their British counterparts. They would have to be constructed under combat conditions, often within range of German artillery. Prefabricated components were being manufactured in Britain, designed for rapid assembly by combat engineers working under fire. Every bolt, every pipe joint, every pump component was being planned with military precision. As 1943 drew to a close, the Hamel project was approaching readiness. The great drums sat in British harbours, their steel pipes coiled like sleeping serpents. The Dungeness pumping station hummed with test operations, its machinery calibrated to tolerances measured in fractions of inches. Across the Channel, the French coast waited, peaceful in the winter light, its rolling hills and quiet fields showing no sign of the industrial transformation that would soon connect them to the heart of British fuel production. The parallel development of WWII and Hamel represented more than just engineering redundancy. It embodied a fundamental truth about the coming invasion, that success would depend not on any single brilliant solution, but on the patient accumulation of dozens of innovations, each solving a piece of the vast logistical puzzle that was Operation Overlord. Across the Channel, by August 1944, the accumulated innovations were about to face their ultimate test. The first WWII's cable lay coiled aboard HMS Conundrum, like a sleeping sea serpent, its flexible steel and lead construction representing months of Arthur Hartley's meticulous calculations. The weather window had opened, a brief respite from the Channel's notorious summer storms that would allow the delicate operation to proceed. Captain Morrison stood on Conundrum's bridge at dawn on August the 12th, watching his crew make final preparations. The ship's specially modified stern housed the massive cable drum, its rotation mechanisms tested and retested. Below decks, SI Appleyard monitored the hydraulic systems that would control the cable's descent rate. Too fast, and the weight would snap the line. Too slow, and changing tides might drag them off course. "Begin deployment," Morrison ordered quietly. The drum began its slow rotation. The WWII's cable, 3 inches in diameter and weighing nearly 2 tons per mile, slipped over the stern rail and disappeared into the grey waters between Dungeness and Boulogne. Aboard the ship, engineers watched pressure gauges and tension meters with the focused attention of surgeons. Each reading told them whether their months of theoretical work was translating into physical reality 20 fathoms below. The crossing took 14 hours. 14 hours of steady progress at precisely calculated speeds, the cable unreeling in a gentle arc across the Channel floor. Radio operators maintained constant contact with shore stations on both sides, reporting position and status every 30 minutes. In the engine room, stokers fed coal into the furnaces with unusual care, understanding that steady power meant steady cable deployment. As afternoon light began to fade, the French coastline grew distinct. Conundrum approached the predetermined landing point near Boulogne, where Allied engineers had prepared a receiving station camouflaged among the dunes. The final phase required the most delicate touch, bringing the cable end through the surf zone without damaging the terminal connections that would link it to the shore pumping station. French resistance fighters, now working openly with Allied forces, had spent weeks preparing the landing site. They had excavated trenches inland from the beach, installed temporary wooden guides to protect the cable from sharp rocks, and constructed a small concrete vault where the underwater line would connect to the terrestrial pipeline network. Their local knowledge of tides and currents had proven invaluable. They understood this stretch of coast with an intimacy no British chart could provide. The cable end broke the surface just as the sun touched the horizon. Allied engineers waded into the shallow water, their hands steady despite the magnitude of the moment. The terminal fitting, sealed and tested in British workshops months earlier, emerged from the Channel like some artifact of industrial civilization, bridging the gap between nations. Cable secure, came the call from shore. Within hours, the first test began. At Dungeness, massive pumps that had been standing ready for weeks began their initial cycle. High-octane aviation fuel, refined in British facilities and stored in underground tanks along the Kent coast, began its journey through the WWII pipeline. The fuel traveled at walking speed through the flexible conduit, pushed by carefully regulated pressure that engineers had calculated to account for every variable. The cable's internal diameter, the viscosity of different fuel grades, the temperature differential between surface and seabed. 24 hours later, fuel began flowing from taps at the French terminal. The moment passed without ceremony. No crowds gathered, No speeches were made. A British technician simply opened a valve and amber liquid flowed into a metal container. But that unremarkable stream represented something unprecedented in military history. The first successful underwater fuel pipeline, delivering the lifeblood of mechanized warfare directly from one nation to another. Within days, the impact became clear. Allied armored divisions advancing through northern France found fuel dumps supplied not by vulnerable truck convoys or exposed tanker ships, but by the steady, invisible flow through Pluto's underwater arteries. Tanks that might have waited hours for refueling could now advance on schedule. Aircraft operating from hastily constructed forward airfields had guaranteed fuel supplies, regardless of weather conditions that might ground transport planes. The success of the first Hayes cable accelerated deployment of the remaining lines. By September, 3 parallel cables stretched across the channel, each following slightly different routes to minimize the risk of simultaneous damage from German mines or submarine attack. The Hamel system, with its rigid steel pipes deployed by the massive floating drums, began operation in October, adding substantial capacity to the underwater fuel network. Bernard Ellis, visiting the French terminal in late September, watched fuel flowing steadily from multiple pipeline connections. The underground storage facility had expanded far beyond its original design. A complex network of buried tanks connected by branching pipelines that carried different fuel grades to various distribution points. Aviation gasoline flowed to airfield complexes. Diesel fuel supplied tank formations and truck companies. Even heating oil reached field hospitals and command centers as autumn temperatures began to drop. The engineering achievement was remarkable, but Ellis understood that Pluto's real success lay in its invisibility. German intelligence had detected increased fuel shipments to invasion forces, but they attributed this to conventional supply methods. More tanker ships, larger truck convoys, expanded storage facilities. The underwater pipelines remained undetected, their steady flow masked by the obvious presence of traditional supply operations. Standing in the buried tank facility, surrounded by the quiet hum of pumping equipment and the soft gurgle of flowing fuel, Ellis reflected on the journey from concept to reality. The initial skepticism from military planners seemed distant now. The technical challenges that had kept his team working 18-hour days through the winter of 1943 had been solved through patient engineering and careful testing. The manufacturing difficulties that had required retooling entire British industrial facilities had yielded to persistent innovation. Most importantly, the human element had proven decisive. The workers who had learned new welding techniques for underwater pipelines, the ship crews who had mastered the delicate art of cable deployment, the French engineers who had integrated British pipeline technology with local infrastructure, the maintenance teams who kept pumps running and pressures stable through the demanding conditions of wartime operation. By November 1944, Pluto was delivering over 300,000 gallons of fuel daily to Allied forces in France. The pipeline network had become a vital artery of the European campaign, its capacity expanding as additional cables came online and pumping stations increased their output. Intelligence reports indicated that German forces were experiencing severe fuel shortages, their supply lines disrupted by Allied bombing and their reserves depleted by months of defensive fighting. The contrast was striking. While German tanks sat immobilized for lack of fuel, Allied armored divisions pressed forward with confidence, knowing that their fuel supplies flowed steadily through the invisible pipelines beneath the channel. The strategic advantage was profound. Pluto had helped transform the Allies' industrial capacity into tactical mobility on the battlefield. As winter approached and Allied forces prepared for the final push into Germany, the pipeline network continued its quiet operation. Fuel flowed eastward through expanding distribution systems, following the advance of Allied armies across Europe. The engineering marvel that had begun with Bernard Ellis's simple observation that pipelines were more efficient than ships had become an integral part of the war's most decisive campaign. In the buried control rooms along the French coast, technicians monitored pressure gauges and flow meters with the same careful attention their predecessors had given to the first test deployments months earlier. The routine had become established, but the significance remained clear. Beneath their feet, through steel conduits laid across the channel floor, flowed the fuel that was carrying Allied forces toward victory. fueling the advance. By September 1944, the network had grown beyond even Ellis's ambitious projections. 4 Hay-IS cables and 2 Hamel lines stretched across the channel floor, their combined capacity approaching what had once seemed impossible, over 1 million gallons of fuel flowing beneath the waves each day. The pumping stations at Dungeness and Shanklin operated in continuous rotation, their Worthington pumps maintaining steady pressure across distances that would have challenged the most optimistic pre-war calculations. Arthur Hartley stood in the operations center at Dungeness, watching the flow indicators with quiet satisfaction. The boards showed all 6 lines operational, fuel moving at optimal pressure toward the continent. What struck him most was not the engineering achievement, though that remained considerable, but the seamless integration of the system into Allied logistics. Pluto had become invisible infrastructure, as essential and unremarkable as the Dover-Calais ferry routes had been in peacetime. The transformation was most visible at the French terminals. What had begun as hastily constructed pump houses near Cherbourg had evolved into sophisticated distribution centers. Underground storage tanks held reserves for the advancing armies, while surface facilities coordinated with Allied fuel convoys moving inland. The Americans had adapted their quartermaster protocols to accommodate the steady flow from the pipelines, treating the underwater fuel as another supply column, one that never required convoy protection or weather delays. Colonel James Morrison of the U.S. Army Corps of Engineers had initially approached the British pipeline project with characteristic American skepticism. Underwater fuel lines seemed unnecessarily complex when conventional tanker operations had served adequately through the Mediterranean campaigns. But by autumn 1944, his reports to Washington praised Pluto's reliability, particularly during the channel storms that regularly grounded conventional fuel shipments. The strategic impact became clear during the September supply crisis. As Allied forces advanced beyond their planned logistics envelope, fuel shortages threatened to stall the pursuit of retreating German forces. Traditional supply lines stretched thin across the expanding front, but the underwater pipelines maintained their steady flow. While truck convoys struggled with extended routes and weather delays, Pluto delivered fuel directly to forward distribution points with mechanical consistency. Bernard Ellis received regular reports from the French terminals, documenting not just fuel volumes but operational insights. The pipeline network had eliminated several critical vulnerabilities. U-boat attacks, which continued to threaten surface shipping, posed no risk to the underwater lines. Weather delays, a constant factor in channel crossings, affected the pipelines minimally. Most importantly, the fuel arrived without requiring dedicated shipping space, freeing cargo vessels for ammunition, medical supplies, and the 1,000 other necessities of modern warfare. The human element remained central to the operation's success. At Sandown on the Isle of Wight, teams of technicians maintained the Hamel drum mechanisms that had enabled the rigid pipeline deployments. Their work required constant vigilance, monitoring for pressure variations that might indicate damage or blockage, coordinating with French operators to optimize flow rates, maintaining the complex pumping equipment that drove fuel across the channel floor. S.I. Appleyard often visited these facilities, observing the routines that had developed around his cable designs. The HAIS lines required different maintenance protocols than the Hamel pipes, more flexible in operation but demanding greater attention to joint integrity. Technicians had developed techniques for detecting micro-leaks through pressure analysis, preventing small problems from becoming major failures. The scale of the operation impressed even its creators. Daily fuel consumption by Allied forces in France exceeded the entire British civilian allocation for motor transport. The pipeline network supplied roughly 40% of this demand, with the remainder arriving through conventional tanker operations. This distribution allowed military planners to use surface shipping for specialized fuels: aviation gasoline, diesel for heavy equipment, lubricants for armored vehicles, while the pipelines carried standard motor fuel for trucks and light vehicles. As autumn progressed, the sight of fuel convoys moving inland from the French terminals became routine. Long columns of trucks, their tanks filled from Pluto-supplied depots, carried fuel toward the advancing front lines. The drivers rarely considered the underground journey their cargo had completed, the passage through steel conduits beneath 60 feet of channel water, the pumping stations that maintained pressure across 20 miles of seabed, the careful engineering that made such transport possible. The German response to Pluto revealed both the project's success and its vulnerability. Wehrmacht intelligence had identified unusual construction activity along the English coast, but failed to deduce the underwater pipeline concept. Luftwaffe reconnaissance flights noted the pumping stations and storage facilities, interpreting them as conventional fuel depots. Not until captured Allied documents revealed the pipeline network's existence did German commanders understand the supply advantage they faced. By October 1944, German sabotage units received orders to locate and destroy the underwater fuel lines. The mission proved nearly impossible. The pipelines lay buried in channel sediment, protected by water depth and Allied naval patrols. Several attempts to deploy divers near the French terminals failed when Royal Navy destroyers intercepted the approach vessels. The underwater fuel network remained secure, its invisibility providing protection that surface installations could never achieve. The operational statistics told the story of Pluto's strategic value. Since the first WWII cable began operation in August, the pipeline network had delivered over 60 million gallons of fuel to Allied forces. This volume represented the cargo capacity of nearly 200 tanker voyages, shipping that remained available for other critical supplies. The time savings proved equally significant. While conventional fuel shipments required 2 to 3 days from English ports to French distribution points, pipeline fuel arrived continuously with no transit delays. Arthur Hartley maintained detailed logs of system performance, documenting not just fuel volumes but operational lessons. The WWII's cables showed remarkable durability, with only minor pressure variations indicating their passage across the channel floor. The Hamel lines required more attention. Their rigid construction made them sensitive to seabed movement, but their higher capacity compensated for increased maintenance demands. As winter approached, the pipeline network faced its greatest test. Channel storms regularly exceeded the conditions anticipated during the system's design phase. Waves above the pipelines reached heights that stressed even the flexible HAIS cables, while tidal movements shifted sediment around the Hamel lines. Yet fuel continued flowing, testament to engineering margins built into every component. The French terminals adapted to seasonal challenges with typical Allied efficiency. Underground storage expanded to accommodate weather-related supply variations, while surface facilities received weatherproofing upgrades. The pipeline network had evolved from experimental technology into essential infrastructure, as reliable as peacetime utilities, as vital as ammunition supply. In the operations centers along both sides of the channel, technicians monitored their gauges with quiet professionalism. The dramatic phase of Pluto had ended with the successful deployments and initial operations. Now came the steady work of maintenance and optimization, ensuring that fuel continued flowing to the armies advancing toward Germany. The underwater pipelines had become part of the war's fundamental logistics, invisible but indispensable to the Allied advance. Decommissioning and remembrance. The war in Europe ended on May 8, 1945. In the operations centers that had hummed with quiet intensity for 9 months, technicians began the careful process of shutting down the pumps. The gauges that had been watched so intently, their needles slowly falling towards zero as the great underwater arteries stopped their flow. Bernard Ellis stood in the Dungeness pumping station on a grey morning in late May, watching his engineers systematically power down the massive machinery. The Burma Oil Company had built something unprecedented here, and now the strategic need that had driven its creation was ending. The pumps that had pushed millions of gallons beneath the channel fell silent, their steady rhythm replaced by an unfamiliar quiet. Across the channel, French technicians performed similar rituals at the receiving stations. The HAIS cables and Hamel pipes that had carried the lifeblood of the Allied advance would soon carry nothing but seawater. Some sections would be recovered, others would remain on the channel floor, monuments to engineering ambition buried in sand and time. The decommissioning process revealed the true scale of what had been accomplished. Recovery teams found that the flexible HAIS cables had performed remarkably well, their innovative design allowing them to flex with tidal movements and bottom currents. Arthur Hartley's months of testing different cable configurations had paid dividends that only became clear during dismantling. The cables showed minimal wear despite carrying fuel under pressure for nearly a year. The rigid Hamel pipes presented different challenges. The steel sections that Bernard Ellis had insisted on manufacturing to such precise specifications had maintained their integrity, but recovering them from depths of up to 180 feet required specialized equipment. Some sections were left in place, considered too difficult to retrieve economically. They remain there still, silent testimony to the urgency that had driven their installation. Cy Appleyard supervised the careful documentation of lessons learned. The Petroleum Warfare Department had accumulated invaluable knowledge about underwater pipeline construction, knowledge that would prove useful in peacetime applications. The techniques developed for Pluto would eventually inform offshore oil drilling operations and submarine cable laying in the decades that followed. But for now, in the summer of 1945, the focus was on quietly dismantling one of the war's most innovative logistical achievements. The secrecy that had surrounded Pluto during its operational phase continued during decommissioning. Most of the engineers and technicians who had made it possible simply returned to civilian careers, carrying their extraordinary wartime experiences as private memories. The workers who had manufactured the cables in British factories went back to producing commercial products. The specialized skills they had developed, the precision they had learned in creating components for an underwater fuel network. These capabilities found new applications in Britain's post-war industrial recovery, but few of their colleagues would ever know about their contribution to the Allied victory. Years passed before the full story of Operation Pluto began to emerge from classified files. Military historians, studying the logistics of the Normandy campaign, gradually pieced together the remarkable achievement. The underwater pipelines had delivered over 172 million gallons of fuel to Allied forces, equivalent to the cargo capacity of nearly 3,000 tanker trucks. More significantly, Pluto had provided strategic flexibility at crucial moments. When German counterattacks threatened traditional supply routes, when weather prevented tanker operations, when rapid advances outpaced conventional logistics, the underwater pipelines had continued flowing. They had been invisible to enemy reconnaissance, invulnerable to most forms of attack, and independent of surface conditions that could disrupt other supply methods. The human cost of this achievement had been remarkably low. Unlike the massive engineering projects that characterized much of the war effort, Pluto had succeeded through precision and innovation rather than brute force. The careful planning, meticulous testing, and patient problem-solving had minimized both casualties and waste. Bernard Ellis returned to the oil industry, his reputation enhanced by successes that remained largely classified for decades. He would occasionally encounter former colleagues from the Burma Oil Company team, and they would share knowing glances, remembering the intensity of those months when they had worked to solve an impossible problem under impossible deadlines. Arthur Hartley continued his career in cable engineering, applying lessons learned from the HIS development to peacetime telecommunications projects. The flexible underwater cables that connected continents in the post-war era owed much to innovations first tested in the Channel between England and France. S.I. Appleyard remained with the Petroleum Warfare Department until its dissolution, then transitioned to advisory roles in the emerging offshore oil industry. The techniques his teams had developed for laying pipelines in challenging underwater environments would prove invaluable as drilling moved into deeper waters in the North Sea and beyond. Today, if you walk along the beaches at Dungeness or Boulogne, there are few visible reminders of Operation Pluto. The massive pumping stations have been demolished or converted to other uses. The specialized harbor facilities have been returned to civilian purposes. The underground storage tanks have been filled and covered. But sometimes, at very low tide, observers report seeing sections of pipe or cable emerging briefly from the sand, remnants of the underwater network that once sustained armies. These glimpses serve as quiet reminders of the extraordinary engineering achievement that unfolded beneath the waves. The men and women who made Pluto possible exemplified a particular kind of wartime heroism. They were not frontline combatants facing enemy fire. Instead, they were engineers and technicians, manufacturers and operators. People who solved complex problems with careful thought and precise execution. Their battlefield was the drawing board and the factory floor, the test facility, and the operations center. Their legacy extends beyond the immediate tactical success of keeping fuel flowing to Allied forces. Pluto demonstrated that seemingly impossible logistical challenges could be overcome through systematic engineering and careful project management. The underwater pipeline network proved that innovation and precision could achieve what brute force might not. In fields of red poppies that now grow over former military installations, in the gentle waves that roll across the channel, in the quiet satisfaction of problems solved and duties fulfilled, the memory of Operation Pluto endures, not as a monument to dramatic heroism, but as a testament to the power of human ingenuity applied with determination and skill. The underwater pipelines carried more than fuel. They carried the hopes of engineers who refused to accept that something was impossible, the dedication of workers who manufactured components to unprecedented specifications, the quiet professionalism of operators who maintained complex systems under wartime pressure. As evening settles over the channel and the lights of ships move slowly across waters that once concealed a revolutionary fuel network, we remember those who made the impossible routine. Their achievement reminds us that history's most significant victories often flow from careful planning, patient testing, and the steady application of human skill to complex challenges. The pipelines of Pluto have long since been recovered or buried by shifting sands, but the example they represent, of innovation serving necessity, of precision overcoming obstacles, of quiet competence achieving extraordinary results, that legacy continues to flow, invisible but essential, through the engineering achievements that sustain our modern world. And a quiet legacy. The pipelines of Pluto have long since been recovered or buried by shifting sands, but the example they represent, of innovation serving necessity, of precision overcoming obstacles, of quiet competence achieving extraordinary results. That legacy continues to flow, invisible but essential, through the engineering achievements that sustain our modern world. In the decades that followed, the lessons learned beneath the channel would resurface in projects that seemed impossible in their own time. The North Sea oil platforms of the 1970s, their engineers drilling through waters far deeper and more treacherous than anything Pluto faced, carried forward the same patient determination that had driven Bernard Ellis and Arthur Hartley through their darkest moments of uncertainty. The subsea cables that now carry our digital conversations across ocean floors, the pipelines that transport natural gas beneath the Mediterranean, the fiber optic networks that connect continents, all bear the quiet DNA of those first experimental lengths of highest cable, wound so carefully in the Siemens workshops of 1943. The engineers who designed these modern marvels may never have heard of Operation Pluto, but they inherited its essential philosophy, that the impossible becomes routine through methodical preparation, rigorous testing, and an absolute refusal to accept that something cannot be done simply because it has never been done before. They learned, as Ellis and Hartley had learned, that the most transformative technologies often work best when they remain invisible, flowing silently beneath the surface of awareness, enabling great endeavors without demanding recognition. Consider the Channel Tunnel, that engineering marvel that finally connected Britain to the continent through solid chalk rather than flexible pipeline. Its planners faced many of the same fundamental challenges that had confronted the Pluto team 4 decades earlier. How do you coordinate massive construction projects across international boundaries? How do you maintain precise tolerances across distances measured in tens of miles? How do you solve problems that arise in environments where direct observation is impossible? The answers they found echoed the methodical approach that had made Pluto successful. Exhaustive planning, redundant systems, and teams of specialists who understood that their individual contributions served a purpose far greater than any single component. But perhaps the most enduring legacy of Operation Pluto lies not in its technical innovations, remarkable though they were, but in its demonstration that the most crucial victories often happen far from the spotlight of public attention. While the world's eyes were fixed on the dramatic advances across France, on the liberation of Paris and the race toward Germany, the real foundation of that success was flowing quietly through steel and lead beneath the waves. 30 gallons per minute, then hundreds, then thousands, an invisible river of capability that made the impossible advance sustainable. This truth resonates through every complex endeavor we undertake today. the software engineers who maintain the servers that keep our digital world functioning, the technicians who monitor the power grids that illuminate our cities, the specialists who maintain the water treatment systems that sustain our communities, all follow in the tradition established by those quiet men and women who understood that civilization advances through the patient accumulation of small, precise improvements rather than through grand gestures alone. The sun sets now over the same stretch of channel where HMS Conundrum once played out her careful dance of cable laying, where the great floating drums of the Hamel system once traced their methodical paths between Dungeness and Boulogne. The waters reflect the same golden light that Ellis and Hartley must have seen on those evenings when they stood on the Dover cliffs, watching their impossible dream take physical form in the workshops below. The fishing boats that pass overhead now have no way of knowing that they traverse one of the most significant engineering achievements of the 20th century. And that ignorance itself is a testament to how completely Pluto succeeded in its mission. For the pipeline network was designed not for recognition, but for results. Not for fame, but for function. Not for glory, but for the quiet satisfaction of problems solved and obstacles overcome through patient application of human ingenuity. In achieving that modest ambition, it accomplished something far more profound. It proved that ordinary people, working with careful attention to detail and an absolute commitment to excellence, could reshape the strategic balance of the world. The legacy flows onward through every project that chooses substance over spectacle, through every team that values precision over publicity, through every engineer who understands that the most important work often happens in the spaces between the headlines. It flows through the graduate students who spend months perfecting algorithms that will make renewable energy more efficient, through the materials scientists who develop stronger, lighter composites for aerospace applications, through the environmental engineers who design systems to clean our air and water with the same methodical thoroughness that once characterized the Pluto workshops. And in the quiet moments of our own lives, when we face challenges that seem insurmountable, when the distance between where we are and where we need to be appears unbridgeable, we can draw inspiration from the example of those who looked across 23 miles of turbulent water and saw not an obstacle but an opportunity, who understood that every great achievement begins with someone willing to work through the details that others consider impossibly complex. The channel grows calm now as the last light fades, its surface smoothing into the mirror-like stillness that comes with evening's peace. Somewhere beneath those gentle waves, buried in sand and silt, fragments of steel pipe and lead sheathing rest as monuments to human determination. Not grand monuments that demand attention, but quiet ones that speak to those who understand the true nature of progress. That it comes not through dramatic breakthroughs alone, but through the patient accumulation of small victories, each one precisely executed, each one building toward a future that seemed impossible until the moment it became inevitable. The engineers of Pluto have taken their place among the unsung architects of our modern world. Their names known to few, but their influence felt by millions who will never know their story, and in that anonymity lies perhaps their greatest triumph. For they built not for recognition, but for results, not for fame, but for the quiet satisfaction of work well done. And their invisible legacy continues to flow through every pipeline, every cable, every connection that binds our world together, carrying forward the patient determination that once transformed 23 miles of impossible water into a bridge of steel and dreams flowing silently beneath the surface of history, sustaining the great endeavors of peace as surely as it once enabled the victories of war, an endless river of human capability that began with a simple recognition that the impossible becomes routine when approached with sufficient care, sufficient patience, and sufficient faith in the power of quiet competence to change the world.